Yes, we can.
Yeah. Okay. So I'll start from the background, then go to summary, and short walk through the post-processing and the data and training and inference methods and some findings. And I'll share like some ideas about how to simplify the approach. And then we will go to question and answers. So I'm computer vision engineer, currently working at Squad. Also, I'm lecturing and teaching computer vision at Ukraine Catholic University, and currently Kaggle Grant Master and competitions. So what I did, basically my approach is the combination of 3D UNet and UNet++ with the EfficientNet B5 encoder. The main thing, the most important, I guess, is the boundary difference over union loss, which helped me a lot in precise segmentation. Also was useful the pseudo labels on external data that was shared by organizers on the platform. Sliding window inference, 3D post-processing based on 2D predictions, and percentile normalization for the input images, and multi-view inference for 2D images and TTA. Basically, the normalization of images were really crucial, and just like I've tried to normalize slice by slice, organ-wise, but it didn't perform well. Later on forum, there was a post about the normalization that let's clip and let's calculate the percentile, and this default values that was presented on the in discussion sections worked really cool, and I used them since that time that I saw, and it really helped me and improved the performance in general for the model. Later on, I discovered the in the paper shared by organizers, the Human Organ Atlas portal, where I saw a lot of images. Two of them were good for this task, and I discovered that one of them is we have in our train set. So the second one could be used as the external data. I also dropped the images with larger resolution because I thought that our private leaderboard and our public will have basically pretty much the same resolution. And later on, organizers proved it. How I pseudo-labeled the data. The pseudo-labeling was on an early stage of the competition, and it was performed using the UNet++ with EfficientNet B5 and B6 encoders. I've tried to create validation based on 3 faults, but the moved to 2-fault validation. The training methods, the 2D model, the training was set up as the multi-view. So I sampled views from different axes, from axial, coronal, and sagittal planes with the same probability. Sampling was based for different kidneys, for different organs. The sampling was based on the density of the labels. So kidney 1 had chance 1, kidney 2 0.65, dense part of kidney 3 1, and kidney sparse 0.85. What to do with the pseudo labels? I decided after visual inspection that they're quite noisy, and I'll place their high threshold for binarization and use pretty much the same threshold as for the kidney 2. During the training, I used zoom augmentation that helped a lot, and D4 augmentation as well. Heavy intensity augmentation helped also a lot to minimize the difference between the leaderboard and my validation. What also I performed, I was sampling only crops from the areas that had non-empty mask for the 2D approach. Useful thing that I discovered lately in the competition was the cut mix augmentation. I've used it at the beginning, but it didn't perform well because I didn't use it in the correct way. So I replaced the random cut mix with the constrained cut mix. I was cutting and mixing the patches from the same plane, from the same organ. So if I'm sampling, let's say, from the kidney 1 coronal axis, the main image, the crop that I will insert inside would be also from the coronal axis from the kidney 1. This worked pretty good. As optimizer, I choose Radam with the Cassin annealing scheduler, and the boundary difference over union loss was used there, modified for the binary segmentation task, because the regional was for multi-class. The output was just a binary prediction. As the inference, I used sliding window from the Monai library, which had Gaussian mixing on the edge of the crop. And for the training, I used two 490 GPUs with PyTorch and mixed precision training. During the training, I used dice monitoring, and I also tried to monitor as well the surface dice, but later on I skipped it because the trend was the same, and the calculation of the surface dice took quite a long time. For the 3D model, I used in-memory dataset to cache everything and to sample effectively. For the sampling, I used binomial distribution for empty and non-empty voxels, and only special transforms for the 192 by 192 and by 192 crop I used. So basically horizontal, vertical flips and random rotations. Zoom performed worse. Intensity didn't boost the score. Probably didn't train enough. For the rest, I used pretty much the same. It was random optimizer with Cassin annealing, and one more thing. This approach was heavily influenced by the NN-UNet architecture, and had the same setup. 1,000 epochs with sampling for like 100 batches per epoch, and 500 random crops for the validation. I tried to run it with the default NN-UNet framework, but it was hard to get not zero predictions on the leaderboard. I don't know why it happened, but like for me, just like running it as it is didn't work. But re-implementing it by myself did the trick. Was the same two-fold setup and two GPUs and PyTorch. Also, like the boundary difference over union loss was modified for the 3D case. What did on inference? Basically, it was the ensemble of two models, but like not just simple averaging, but in a better way. So both models used sliding window inference. For the 2D model, I performed multi-view inference and D4 TTA. To fit into the memory and not like get out of the memory ever, I use TensorDict library to handle large memory footprints for the 3D data. It's from the PyTorch extension, currently in beta. Also, important thing, I saw that I'm getting better performance if I'm running inference on the bit larger resolution, not upscaling, just getting larger crop. So I trained my model on 500 by 500 crop for the 2D model, but inference was performed at 800 by 800 resolution. At the same time, while 3D model was trained on 192 resolution and inference was performed on 256. Yeah, one thing more, how was performed the ensembling. So based on the 2D model predictions, I generated the bounding mask around the vessels. And this mask was applied on top of the 3D model predictions. Since I saw that on my 3D model predictions, I'm getting false positives outside of the kidney, and I saw that if I'll train my model with the auxiliary output of kidney volume, it could improve the performance. But I didn't like. I decided to go with a simple way since I have quite good model for 2D segmentation, and I just could get the bounding mask and apply it on top, and then average what's inside. What was important, boundary difference over union loss worked really good for both 2D and 3D approach, and it beat the dice focal loss, binary cross entropy, whatever standard. Basically, I guess the half of the competition I spent on trying to improve the loss with some addings of focal non-symmetric stuff that could improve the performance for sparsely annotated data. What interesting was also that on my validation, the threshold optimal was around like 0.15, 0.2. But on the leaderboard, I discovered that lowering the threshold improved the metric. And actually, on public leaderboard, the optimal threshold was around like 0.05. But for the private, the threshold was even lower. I guess it's related to the sparsely annotated data and not the metric that was scored on the leaderboard. What else important, that validation was almost blind. And as I can see from the previous speakers, it was not only for me. So basically, the lock is important, but like the stability for both private and public is also important. And what else? The 3D model failed to distinguish kidney volume and background, which caused false positives. And to reduce them, I used the 2D model predictions. Yeah, what else important is that if to use not two-fold approach, but the single-fold approach, the 2.5D model, I could reach like 0.75 on the private leaderboard and 0.87 on the public leaderboard. The 2D model ensemble of efficient net B5 and B6 with UNet++ decoder without validation scored 0.77 on the private leaderboard, which was also not selected for the final submission. And the top single 3D model, the same dynamic UNet, which is basically the simple 3D UNet, same as inside of NN UNet framework. On the correct fault, scored 0.75 on the private leaderboard and 0.86 on the public leaderboard, which also quite good. And but unsambling predictions of the second fault reduced the score. So that's pretty much it. Thank you for your time, and I'm waiting for your questions.